I'm going to talk to you about work that Ido Erev and I have conducted together and separately over a number of years. Ido is over there, so the plan is that I'll actually talk for both of us, but that he'll answer questions. This is work that, of course, my talk may be abbreviated. Well, okay, this is work that we started together some time ago, so I'll start by telling you about an older stream of work in which we looked at learning in games. So I'm not going to be talking to you about evolution, but about learning. But the thing about learning in games is that players learn about the game at the same time as other players are learning about it, and so what they learn about the game depends on what others are learning. So there's a kind of co-evolution of learning going on. And we'll tell you about some success we had in explaining some things with simple reinforcement models of learning that if you wanted, you could think of as being like discrete time replicator dynamics. I won't talk in detail about the models. In fact, Ken Binmore has done some work on that years ago about using replicator dynamics. And then Ido and I went in different directions from that. He decided to look at radically simple environments in order to study individual learning in its clearest form without complications. And I got caught up in trying to design complicated economic institutions. But our work has some convergence now. In particular, one of the things that Ido and his colleagues discovered is that how people learn depends a lot on how they experience the environment. So I'll talk to you about that. And that'll bring us back to the question of how do economic institutions work well, and why do models of highly rational calculating actors often provide very good approximations when we don't think that that's what individuals are actually doing. So to put it another way, a lot of economic models are models of equilibrium. Again, this fits with the discussion of replicator dynamics. But mostly we don't have very good models of equilibration that we think actually describe what goes on in the world. But what we observe is that some games move quickly to equilibrium and some games move much more slowly, if at all. And so what we'd like a learning theory to do for us is help us predict which of those will be which. So let me tell you about two games, which may already be familiar to many of you. They're similar in various ways. They're similar in the way they're played, their structure, and they're similar in their perfect equilibrium predictions. So the first game is the ultimatum game, and it's a two-player game where each player has one move. Player one proposes a division, how much he should get and how much player two should get. So typically you say to player one something like, you have $10, divide it between you and player two. Player two can either accept the division proposed by player one, in which case they each get the payoffs that player one proposed, or he can reject it, in which case they each get 0. So there's a simple argument that says if they only care about how much they get, then player two is going to look at this and he could get 0 or x2. As long as x2 is not smaller than 0, he'll accept. Therefore, player one, knowing that whatever offer he makes will be accepted, can give a very small amount to player two and take the rest for himself. But that's not what we observe in the laboratory. On the contrary, what we observe is that player twos who are offered very small amounts tend to reject them. And of course, it's not very costly for them to reject them because they're being offered a very small amount. Now here's another game, which is a public goods game. We've heard some public goods games discussed already, but this is a very extreme public goods game. But it's similar to the ultimatum game, not just in that its equilibrium will be extreme, but that it's a two-player game. Each player has one move. Player one chooses a quantity of the public good that he is prepared to supply. Player two learns this quantity and chooses a quantity himself. And then there's a total public good that's supplied. I'll come back to that in a minute. But the payoffs to the players, they get some reward for the total public good minus the cost of how much they provided. But how much is what is the total public good? The reason this is called a best shot game is the total public good is the maximum that player one or player two provides, the best shot. And what that means is that the contribution of one of the players will be always totally wasted because it won't contribute to the total quantity that exists, but it will be costly to supply. So there aren't going to be equilibria in this game where both, not going to be perfect equilibria, where both players provide a positive amount. Only one player will provide a positive amount. Whoever provides the larger amount determines what the rewards are, and the smaller amount is completely wasted, but it's costly to provide. So in the parameters that we're going to be using, costs 82 cents, I think, is that right? Yeah, per unit. So when you look at the redemption values of the units, what will make sense, player one goes first, remember. So he has the option of being the one who provides nothing. He can provide 0, which is what he does at the perfect equilibrium. And player two is left to decide how much to provide. If he's simply calculating how much to provide, he should provide 4 units because the marginal cost of the 4th unit is, the benefit is above 82 cents, the cost is 82 cents. And so the equilibrium is a very unequal equilibrium. Player one will provide nothing. He'll get the benefit of 4 units. Where am I? 4 units, so he's going to earn $3.70. Player two will get that same benefit, but he'll have to pay for the 4 units. He's only going to earn 42 cents. That's a 9-to-1 ratio. When we see ratios like that in the ultimatum game, they get turned down, they get rejected. So of course, in the best shot game, one thing that could happen is player one will provide 0 and player two will provide 0. By and large, that's what happens in the ultimatum game when player one proposes that player two should get something very small. But that's not what we see. In these two similar games, here's the ultimatum game results. And the equilibrium prediction, remember, is that player two will get something very small and accept it. But what we see is in the first periods, player ones propose on average almost half, not quite 40, not a little more than 41%. And in the 10th period, there they are, still on average giving around half. So player ones, for whatever reason, in this ultimatum game, we'll talk about it, they are not proposing that player two gets nothing. They're proposing that player two gets almost as much as they do. Now, here I'm going to look at the best shot game under what's called partial information. This means that the players do not know each other's payoffs. They only know their own payoffs. Okay? And I'll show you under full information in a moment. So under the best shot game in partial information, player one, the prediction, remember, is that player one will provide a quantity of 0. But in period 1, he starts out providing quite a bit on average. But by period 10, the average quantity is less than 1. Right? So many player ones are providing 0. You have to provide discrete integer units of quantity 1. And these are well, let's take a look at what happens. But I'll show you the player two's decisions in a minute. But one thing you might wonder is what will happen in full information. In other words, these are pretty different. Player one is providing very little as predicted by equilibrium in this game. He's providing a whole lot contrary to what's predicted by equilibrium in this game. But in this game, they don't know the other player's payoff. So if the motivation is considerations of fairness, those just can't operate in the partial information game. But if I start to inform the players of the other player's payoff, then maybe if it's fairness that makes payoffs equal, maybe they'll become equal in the best shot game. But that's not what happens. When the players know each other's payoff, player ones start off offering a bit less, but they're still offering a positive quantity, but they quickly get down to everyone offering 0, 0 with 0 error. So they go, the player ones learn to provide 0 units of the public good when they know the payoffs of both players. Okay, so let's quickly take a look at sort of scatter diagrams of the data. Here's round 1 of the partial information game. And what you see is there's plenty of people providing, both player 1 and player 2 are providing some units of public good. That's wasteful. Okay, it's inefficient. But very few player 1s are providing 0 in the first period. But by the end, by round 10, no pairs are both providing positive quantities, and lots of player 1s are providing 0 units, and many player 2s are responding by providing 4 units. And here's the full information condition. What you see is that even at period 1, lots of player 1s are providing 0, starting initially, and by the end, again, no one there are no joint provision of wasteful amounts of quantity 1 and quantity 2, and lots of player 2s are not responding with 0, but they're responding with the perfect equilibrium response, which is they provide 4 units. So these are games that are similar to each other but go to different equilibrium. Here's the ultimatum game data. In round 1, player 1 is offering a lot of 5s out of 10, a lot of 4s out of 10, some small numbers. The lighter numbers indicate some of those offers are rejected. By the end, very small offers are not being offered anymore. Offers less than 5 are still sometimes being rejected. And what we see at the end is not that we've gone to equilibrium of offering 0, but that, in fact, the mode is a pretty fair offer between player 1 and player 2. So these two games are pretty different from each other in their outcomes, but they look pretty different in their format and in their equilibrium. So what's going on? Well, one thing that's going on that this summarizes a lot of data is in the ultimatum game, if you were giving advice to player 1 and you looked at the revenue that accrued to player 1 by offering different amounts x2, what you'd see is that the maximum payoff to players 1 come when they offer 50%, when they offer 5 out of the $10 to player 2. That's something that very seldom gets rejected. Everything else, well, I don't think offers of 6 got rejected, but when you offer 6, you only get 4 yourself, so you make less. And if you offer only 1 to player 2, when he accepts, you make a lot of money. You'd make 9, but he rejects often enough that your expected return is less. On the other hand, in the best shot game, the story is very different. When you offer the equilibrium amount, you get your highest payoff, because as soon as you offer a positive amount, it becomes profitable for player 2 to offer 0. Remember, it's wasteful but costly to provide this public good. So player 1s who provided positive quantity found that player 2s didn't provide a positive quantity, and that therefore their payoff was very low, and that eventually their largest payoff came from offering 0. So that's a learned response. These games don't look that different in the first period. But the difference we propose, it has to do with the feedback you get off the equilibrium path. Player 1s who make close to the equilibrium offer, they offer very little to player 2 in the ultimatum game, they get rejected. And when they deviate from the equilibrium offer, they get a higher payoff. Player 1s in the best shot game, when they deviate from equilibrium, don't get rewarded. They get a very low payoff, but they get a high payoff when they stick to the equilibrium. So reinforcement learning models do a pretty good job of explaining this. And again, I won't go into the details of different reinforcement learning models, but we look at discrete time models that track the game, but you can think of them as if they were replicator dynamic models. And what goes on in the ultimatum game is that proposers learn not to make small offers much faster than responders learn not to reject them. So if you go back to the data, what you see is there are no more small offers, but there's still offers being rejected if they're less than 50-50. And it makes sense that that should happen, because when you reject a small offer, it doesn't cost you very much. So you don't learn very quickly not to reject small offers. But when you make a small offer and have it rejected, that costs you a lot. So you could learn quickly in these models to not make a small offer. On the other hand, in the best shot game, player 1s don't get much reinforcement from deviating from equilibrium, so they learn to free ride. They get higher payoff on average when they provide 0. And then player 2s learn to provide 4. So we converge to equilibrium there. So we need a theory of learning that would maybe be more robust than the ones we had been using in those days. And I want to tell you about those. And what we'd like a theory of learning to do for games is tell us what players will learn from the feedback, and also, incidentally, how the information about the game changes something like the best shot game. Right? So we see a different kind of convergence from a different initial distribution in the best shot game than with full information than without information about the other's payoff. So these reinforcement learning models, like replicator dynamics, don't have a place to put that information, that difference. The way it shows up is different distribution of first period behavior that appears through some kind of cognition that players have when we give them more information. And then the reinforcement learning dynamics do a good job of picking up from this new, different initial distribution. So one question is, how do these initial different distributions come up? And so what Ido and his colleagues did is they started looking at very simple choices over lotteries. But instead of doing what became famous through the approach of Kahneman and Tversky, instead of describing the lotteries to the participants in their experiment verbally, telling them what the probabilities were, they just let them experience the lotteries, gain experience by playing the lotteries and seeing the outcomes. So they have a quote in one of their papers that says that describing the lotteries, saying, here's a lottery that gives you a 10% chance of this payoff and a 90% chance of that payoff, that became the fruit fly of choice research. And it sort of drove out other kinds of experience that we might be interested in studying. So what they started to do is that they simplified a great deal, and they said, let's just look at experiments where all you're going to do is push two keys, one of two keys. And your task is to click one of these two keys, and when you do that, you will see the payoffs that you got from the key that you clicked, and also the payoff that you would have gotten had you clicked the other key. So your feedback after a trial of this experiment, which you can, of course, do very many trials, would say you pressed the right-hand button, you got a payoff of a dollar, or maybe it's a shekel. Had you pressed the left-hand button, you would have gotten 0. That's what you learn. And now, rather than being told what the probabilities are that generated those numbers, you're just going to be invited to push them lots of times. And we'll see how your behavior evolves. So what they find is that while in many circumstances this leads to behavior that looks like maximization, there are regular circumstances in which it does not. So for example, here's a pair of buttons. One of them gives you 0 with certainty, and one of them gives you a 10% chance to lose $10 and a 90% chance to win $1. So it has a negative expected value, but it's being picked more than 50% of the time over, these are blocks of, maybe these are 500 periods, is that right? Okay, so over 100 periods, you are not learning that this is a bad gamble. On the other hand, here's a good gamble. Here's a similar one where you can get 0 from one button in this lottery from the other. 10% chance you win $10, 90% chance you lose one. It has a good expected value, but they only get up to about 25%, a little higher than 25% of choosing that. So they're not maximizing expected value. And what it looks like is that they're underweighting rare events. That is, you're learning from experience. You never see this number 10%. You just only win $10 10% of the time. And what it looks like you're doing is you're saying, you know, I don't win very often. I mostly lose $1, whereas I could get 0 for certainty if I push the other button. And here you're saying, you know, I rarely lose $10. I'm mostly getting $1, whereas I'd get 0 if I got the other, so I'll stick to this one. So these are non-expected value maximizing decisions, and they look like you underweight rare events. And one reason that's important is Kahneman and Tversky developed a whole theory of how you would choose these lotteries, among these lotteries, if they were described to you. And what they found is you overweighted rare events, right? They found just the opposite. So they found that if they described to you, you know, a small probability of losing $5,000, you know, in a hypothetical choice, you would choose losing $5 with certainty. And if they gave you a small chance of winning $5,000, you would jump at the chance. Even when you were facing things with the same expected value. And they attributed this, and they built into prospect theory. The idea is that you look at small probabilities and you overestimate them. But what Didot and his colleagues found is that when you're looking at these from experience, that is, no one shows you the probabilities, you just play the game and learn what to do, you do the opposite. You seem to underestimate the low probabilities, and they referred to this as the experience description gap. So you can start to see where I'm going. In the best shot game, we're doing some description and some experience when we tell you what the other player's payoffs are. That's the description of the game, and then there's the experience of playing the game. So you can see these things in very controlled ways in this simple environment with the same decision. So they describe to you the lottery, and then you get to play it many times, 100 trials. And what you see is, here's a lottery that has a 1/20th probability of giving you a reward. So it's a good bet. It's a 3.2 expected value compared to getting 3 all the time. And you react to that. It looks like a big probability, and you choose it more often than not in the first trial, but less often by the time you've played 100 times, even though it has a higher expected value. You, after all, aren't very often getting the big reward. You're mostly getting 0, whereas you could have been getting 3 with certainty. So that's a hard choice to make. It's hard to be that disciplined. Here's a study by Greg Barron and Steve Leiter and Jen Stack. One of those people was Ito's student, and the other 2 were mine. And what they do an interesting experiment with similar lotteries. They say a certain gain of 10 cents versus 13 cents with a very high probability, and a big loss, $15 with probability 1 in 1,000. A small enough probability that people are not going to experience it in the 100 trials that they're going to have. But they have two conditions. In one, they describe the game to you at the beginning. They give you a warning right at the beginning, and then they say, now you can play. You can play 100 trials and get the payoffs. And here's the curve. The probability of taking the risky action starts off lower than if they don't tell you about that probability. So that's not surprising. But then after 50 trials, they tell the other group. They say, you've been playing this game for a while. You haven't experienced that $15 loss, but there's a risk that you will. We didn't tell you about this, but now we're telling you. So starting in trial 50, the two groups have exactly the same information. They've seen the same sequence of random events, and they've gotten the same warning. But they got it in different order. These guys got the warning at the beginning, and these guys got it at the end. And they don't converge. They stay different. And the way one of the things they were thinking about when they did this experiment was there was a pain medication called Vioxx that was discovered to increase the risk of heart attack. And new prescriptions just fell to the floor. No one wanted to take a pain medication that increased the risk of heart attack. But people who were already taking Vioxx, who'd found that aspirin didn't work for them and that this worked pretty well, they liked to keep taking it. Right? They hadn't had a heart attack. It worked for them. It was a good medicine. And so their behavior, the guys who got the experience before the warning were different than the guys who got the warning before the experience. So there's something going on there. People are complex, and even after they have the same information, how that information has accrued to them changes the way they learn and what they conclude. Now, one of the old things about, one of the old observations about learning was variability sometimes slows learning. But here's another look at that, which says many of the things that in the Kahneman and Tversky framework look like risk aversion. You switch from picking the action, you could get 0 for sure, or you could get an action that gives you 1. Well, everyone learns to choose to maximize. If you, instead of getting 1 for sure, you get this gamble that has expected value of 1, it's a lot harder to learn to choose that gamble compared to getting 0. So only 58% of people are choosing it over time. But you could interpret that as risk aversion or loss aversion. But here you see it the other way. If you were risk averse or loss averse, then when you go from -1 to this -1 gamble that has much more variance, you should drop away. But in fact, these numbers are pretty similar. And what seems to be going on is that variability, it's harder to learn about a gamble that has high variance. So let me show you something that my colleagues and I did in games again, in a more complicated environment, because I want to talk to you a little bit about this coevolution of learning. So I want to tell you very briefly about 10-period prisoner's dilemma games. So I'm going to guess that everyone knows what the prisoner's dilemma is. What the 10-period prisoner's dilemma is, you're going to play 10 repetitions of the prisoner's dilemma with the same person. And then you're going to be matched with a different person and play 10 repetitions of the prisoner's dilemma with that person, and so forth. Okay? And you can do that 20 times. So you're going to play 200 experiences in groups of 10. And as I say, the hypothesis we want to look into is that variance slows learning. And what you have to learn in a 10-period prisoner's dilemma is that you'll make more money over the 10 periods if you start off by cooperating and cooperate for a while. Okay? So here's so one condition of the experiment was these payoffs are, you're going to accrue monetary payoffs. We did these, for historical reasons, we did them in numbers that related to roulette probabilities. But these aren't probabilities. These are, if you choose A and the other place chooses A, you will each get 10.5 cents credited to you. And after you've played 200 rounds, you'll get paid your accrued amount. And in this, you're going to see not just what you get paid, but you're going to see that you chose A and the other chose A. You're going to see what everyone did. But the other condition, the next condition of the experiment is instead of getting paid 10.5 cents, you're going to have a 0.105 probability of getting $1. Okay, and that'll be independent of the other guy's probability. You'll still see what he did. You might not get the good payoff, but you'll see that he cooperated. If he cooperated, you'll see that he defected if he defected. Okay, so in this condition, they see the same matrices, but the payoffs are probabilities. These payoffs are probabilities, and what they see here are zeros and ones. You either get $1 or you get 0. So sometimes you will both have cooperated, but you won't get the cooperation payoff. Okay? So here are the some deterministic data, and I'm showing you these by trials rather than an aggregate to show you that we're seeing a very robust phenomenon. Okay, in blue, I have rounds 1 to 5. So in rounds 1 to 5, actually a lot happens in those 1 to 5, so there's already learning in the first 5 trials. But what you're seeing is pretty high cooperation in round 1, trailing off to lower cooperation in round 10. And then the whole curve shifts, it tilts, so that probability of cooperation gets really high in round 1, as people learn that if you cooperate in round 1, the other guy will cooperate in round 2. And you can keep that up for a while, but in fact, cooperation drops off a bit by round 10. By round 10, the other guy's going to be defecting. So that whole curve shifts. You're learning to cooperate as the other player you're playing with learns to cooperate. And that happens every time we do it. These are the conditions with the probabilistic payoff. And there's just no learning, right? There's somewhat declining cooperation as you go along, but it's the same in the first 5 games you play as in the last 5 games you play. They just fail to learn to cooperate. They don't learn those high cooperation. So this looks like a win for the hypothesis that variance slows learning. To learn to cooperate in the prisoner's dilemma, the repeated prisoner's dilemma, the person you're playing with has to also learn to cooperate, because what makes your cooperation valuable to you is that it elicits their cooperation. If they are not learning to cooperate, then it won't be valuable to cooperate, and you shouldn't learn to cooperate. Okay? But there's another hypothesis that you could go on, which is maybe variance just makes cooperation less desirable. Maybe it's less fun to cooperate if sometimes I get $1 and you get 0, or vice versa. But it turns out you can control for that by by rematching every period. So you're playing 1 period prisoner's dilemmas. And when you do that deterministically, what you see is that you get a reasonably high rate of cooperation, but it deteriorates pretty quick to some base rate of 10% or so of provision of public goods, just out of good feelingness. Now, if random payoffs made cooperation less desirable, then we should see less cooperation when we give them random payoffs. But if it just slows learning, then we should see more cooperation, because what they're learning in this game with deterministic payoffs, they're not learning to cooperate, they're learning not to cooperate. And in fact, we see more cooperation. They learn more slowly not to cooperate. They get there, but it takes them longer. So this is coevolution of behavior in the game through learning. And when we slow the learning in this game, we make it go away. That is, instead of slowly learning to cooperate, there's actually no point in learning to cooperate if your partner is not learning to cooperate. The benefit of cooperation comes only from cooperation. Okay, so there are turns out Ido's observation, Ido and his colleagues' observation that there's this big experience description gap has a lot of consequences that follow from it. Here, I won't talk more about this, but this just shows in some very simple artificial commodities that index funds, it's hard to learn to love index funds. They have lower variance than the underlying stock, but it's very tempting to follow the underlying stock to chase big returns and flee from past losses. But what turns out to model this behavior well, this description gap, is predicting from small samples. So here's the list of the gambles I've showed you so far, and their expected value. You can always get 0 by choosing the status quo. And here's what people have learned. But here are the predictions from a model which says you get a sample, you look at a sample of past actions, and from that small sample that might have 4 or 5 observations, you pick the best one and go from there. So just incidentally, one of the things that I've collaborated with Ido on is we've run competitions, open competitions, where we present some experimental data and invite people to model it and to predict a prediction set, a different set of experimental data drawn from the same distribution of games in the same population. And we ask people to submit programmed models that will try to predict these data. And the ones that work well tend to have small samples. So this seems to be, there's some reason to think that may be what's going on in some of our data. So why might people choose to use small samples? Well, one, of course, is bounded rationality. right? It might be really hard to remember 500 periods of play and figure out the best thing to do on the basis of them. Another might be, in these very simple things where you just learn from experience what's going on, Ido certainly doesn't promise you that you are dealing with a stationary distribution and has run some experiments where you're not dealing with a stationary distribution. And if you at all suspect or want to explore the possibility that you're not dealing with a stationary distribution, then small samples of similar things might be very relevant to make your decision. So one of the things you can look at is how do people choose those samples? If they're using small samples, what kind of pattern recognition might they be using to try to find good samples? So for example, here's a series of, you can push 2 buttons. You push this button or this button. On the first trial, this one yielded -1 and this one yielded 0, and the second and the third. But on the fourth, this one yielded 2 and that yielded 0. 3 more -1s and then a +2, 3 more -1s and then a +2, 3 more -1s. What do you choose now? Well, a lot of us and a lot of the experimental subjects would say, looks like we're due for a 2, right? And pick a 2, even without the colors, right? That's a pattern that looks regular enough. And it doesn't have to look that regular, even after just one experience that after 3 -1s are a 2, a lot of people will go for the 2 after 3 -1s. So, and depending on what the underlying generation function is, that might not be crazy. So among the experiments that have been done are experiments where the numbers are generated in a non-stationary way by a Markov process that changes states, and that as you get -1s, it changes states and makes a +2 more likely. So here is some data from such a thing. Here's a lottery with independent trials of -10 or +1, and people don't take that very often. But here's one where there's some predictability. You get a -10 every 8 or 10 trials based on this underlying unobservable Markov process. And people get pretty good at picking this, and they get pretty good at picking it when it's good to pick, right? When the deck gets too rich, they go away from it and come back to it when it looks like it'll pay off. So, a little bit like counting cards in blackjack. You know that the distribution isn't entirely stationary. You could learn to do something with that. Okay, and again, so this is actually the experiment I was just talking to you about. This is a 3-state Markov process, and subjects learn to play it pretty well in the sense that when there's going to be a +1, they choose it a lot more than when there's going to be a -10. But what you're seeing here is, depending on the probabilities, whether or not they learn to maximize, whether or not they learn to choose the high expected value gamble changes a lot. And one of the things going on there is the underestimation from experience of small probabilities. Okay, so right now we can't tell you very much about how people choose similar situations, how they choose a sample of similar situations. But it seems likely, current hypothesis from this kind of work, is that people do that not in a crazy way and then react based on past experience. So, so the question of what can we say even without knowing the exact nature of this is how I want to come back to the larger economic questions that motivate this, which is how can we think about different economic institutions that will help people learn to behave in sensible ways. So, rare and unpredictable events are important, right? So one of the things that you can study, for instance, is things like, flood insurance. Do we underinvest in flood insurance because year after year there's no flood and then there's a flood? And if we think that's what's going on, then how can we change the information we give to people about insurance and the risks they face? Similarly, wearing seatbelts or investing in bubbles. And so my work has been sidetracked in recent years into trying to design institutions of various sorts that'll promote welfare. And so right now, the way our thoughts are coming together on this is, often the institutions we design are well modeled as if, we think it's a good approximation to treat people as if they were rational. And the question is, why is this? It seems to be that learning and rational models will say something similar if the experience, if the thing you get that maximizes your welfare also often gives you a good outcome, right? So that doesn't have to be the case, but what you're good at learning are things that happen a lot. What you're bad at learning are things that happen seldom. And so the question is how to create the experiences that will give you the right kind of feedback. So for example, one of the things my colleagues and I have been doing over the years is designing school choice mechanisms in American cities. And the school choice mechanisms that we've been designing for New York high schools or for Boston schools or in Denver and New Orleans have the property that families are asked to give preferences over schools. And it turns out that, in contrary to past ways of doing this, the new mechanisms that we use make it a dominant strategy to reveal your true preferences. They make it safe to confide to the school system which schools you would really like, even if you have only a small chance of getting into them. Now, when we introduced this in Boston some years ago, we were replacing a system in which you came to great harm if you didn't get the school that you listed as your first choice. And therefore, you had to be very careful about what school you claimed was your first choice. So these are subtle differences, and you could hardly expect people to learn them from experience. So the description is going to matter, too. That is, part of the design job is not just to design something that will, over time, give good incentives so that when people talk to their neighbors, they'll get reinforced to do the right thing, but to give a description, a communication package that will allow them to know that the world has changed and that the advice they used to get is no longer accurate because there's a new mechanism. We want to start them off, properly in a new period one. So when we first rolled out the Boston school choice mechanism, there was a brochure that went out in backpack mail. You send it home with kids and things like that. And on some page in the middle of a big booklet, it explained what I just said to you. And then it said, if you have any questions, here's a telephone number you can call. And the telephone number rang on the desk of a man named Carlton Jones, who was an employee of the Boston Public Schools and who understood very, very well the differences between the old and the new system and the good properties it had. And so he started getting calls that he said were a little tentative. People would call him up and they'd say, I'm calling because on page 6 of the brochure, if I understand it correctly, it seems to say that it's safe for me to list the true choices of schools, even if we have only a low chance of getting them. And he'd say, that's right, you've understood correctly. And they'd say, because the reason I ask is we went to the Family Resource Center, and the nice ladies at the Family Resource Center explained to us that we had to be really, really careful what we put as our first choice, which had been true the previous year. Okay, so what had the glitch that had happened in the first year of the rollout of the Boston school choice was that the description didn't match the new environment. And now when we talk to American cities, we tell them not just we'll help you design an algorithm, but we'll help you design an algorithm and a communication package. So one thing that we're trying to learn from this is how do those things go together? If they used to tell people in Boston that they should put down their true preferences, but people pretty quickly discovered through the experiences of friends over the years that wasn't a good idea, that was bad advice. So people learn. You can't expect them to put down their true preferences when you're going to harm them if they do. But on the other hand, it's hard to learn that the system has changed and it's now safe. Okay, that's a very hard lesson to learn. Let me mention that how you learn things like that can also depend on the kind of feedback you get. So this is my last slide. Here's a graph of some experimental results from some different kinds of auctions in a laboratory experiment. And what I'm graphing here, sorry, the axes aren't labeled. What I'm graphing here is time, repetitions, and here I'm graphing what percentage of people's true value they are bidding in the auction, and it's 100% up here. And the different auctions are a bunch of auctions motivated by eBay and other iterative mechanisms where you bid if you're not the high bid. If anyone wants to bid more, you can bid more. You see whether you were the winning bid or not, and so forth. And they're comparing it with the second price sealed bid auction. Now, the second price sealed bid auction, the way that works is you write down or enter on a screen the bid you want to make. The auctioneer opens them up. The high bidder wins and pays the second highest price. And it's not hard to show that in a private value auction of the kind we were talking about here, it's a dominant strategy to bid your true value. Because, of course, you don't pay your bid. Your bid just determines whether you win or not. What you pay is the second highest bid. And that, together with some other things, makes it a dominant strategy. But it's hard to learn that. So here you see that, so it's a dominant strategy. This is the only of these auctions where you have a dominant strategy. It's a dominant strategy to bid 100% of your true value. But it takes a long time to learn that. Why is that? Supposing you think that maybe it's smart to bid less than your value. In many kinds of auctions, that is smart. Well, you bid a low value, you lose the auction, but you don't discover that until the auction is over. Now you have a second auction, you bid higher, and so forth. Whereas in these auctions, if you start off with a low bid, then you're not the high bidder. And the auctioneer says, does anyone want to bid again? And you say, I do. You know, that object is worth a lot to me. I started with an initial high bid, but I immediately understand in the court before the auction is over that that's a mistake. I get feedback that allows me to see that I can't win a valuable object for a low price. I have to pay more. So in these auctions, although it's not a dominant strategy to be bidding your true value, they learn much quicker to bid their true value. There's a related result here that says you should keep going until you get to your at least higher than the second highest price. So these two mechanisms, if you wanted to analyze them as if people were very smart, you would not predict that there was a difference between them. And if anything, if people were really, really smart, they would the dominant strategy argument should convince them. But in fact, people form impressions about what to do, and then they adjust them based on their feedback. So both the description and the experience matters, and other people's experience matters when you're playing with other people. So when you do market design, when you try to design new economic institutions, whether they're school choice or labor market clearinghouses, or my colleagues and I have been building kidney exchange mechanisms over the last couple of years, whenever you start, the mechanism is new. So there's no reason to think that people will start immediately at equilibrium. They're going to have to learn what to do by experiencing the mechanism. And one of the things you want is, in practical market design, is not just to have a good equilibrium, but you want to make sure that people don't die while getting to it, that it has good properties on the path to equilibrium. Stop there.